Hello my friends, today we are going to talk about Compton's effect, how it occurs, and how to derive Compton's shift equation. Now, when a wave is produced, like let us say this is a source of an X-ray. When you produce an X-ray, it moves with a certain wavelength. Let us say the wavelength at which this signal or X-ray is moving is lambda. Then this wavelength, this X-ray has been directed towards a target. This target can maybe be a graphite or maybe an electron. It will interact with this target and then it will be deflected. This X-ray which was moving, it will be deflected. Now, the wavelength of this X-ray will be different from the wavelength at which this deflected X-ray will be moving. Now, what might be the reason? Let us say when the X-ray has been produced at this point, it moves with a higher energy. That means its frequency will be high. And then if the frequency is high, of course the wavelength will be what? Wavelength will go down. Now, after hitting the target, some of the energy which were contained in these X-rays will be lost. Therefore, the energy at which the reflected X-ray will be low, to mean its frequency will reduce. And therefore, if frequency has been reduced, its wavelength will increase. So we are seeing that the wavelength of this incident, let's call it an incident X-ray, and this one is reflected. After interacting with the target, the wavelength increases as compared to the incident X-ray. So you are seeing that this reflected X-ray, let's give it a wavelength of lambda prime. So the wavelength here is lambda and the wavelength here is lambda prime. Now we are seeing that this X-ray has been deflected in a certain angle. Let's give it a name, theta. Okay, I hope we are together. Now, in this experiment, we know that the intensity and wavelength of the incident beam, and for a given scattering angle, this one, we measure the intensity and the wavelength of the scattered beam. You should measure the intensity, that is its strength, and its wavelength after it has been what? It has been reflected. Now, let us see how we can derive the Compton's shift equation. Let us see how we can derive the Compton shift equation. And we need to know some of the things, like for the incident X-ray or incident radiation, for the incident radiation, let's say it has an energy E, and then from there we know that when this particle, this X-ray is moving, it has got a momentum. So let's say it has got momentum P. Let us say PF, because it's moving with a certain frequency. And then now After collision with this target can, I've said that it can be a graphite. This graphite has got valence electrons. It has electrons, not valence electrons. It has electrons, so it depends. This electron can be valence or they can be fixed. So after collision, these electrons will gain some energy. We've said that this X-ray is moving with a certain intensity. It has got some energy, and when it strikes this target, some energy is lost, resulting to this reflected X-ray or radiation moving with a low frequency. So the electrons which are here will be hit, and after interaction of electrons and X-ray, we will have a reduction in energy. That means electrons in this target will acquire those energy which were in this X-ray. So we say that for the electrons, we have energy. Let energy be E, and then let momentum how do we write momentum? Yeah, momentum. Sometimes you can read many things to an extent of forgetting even spellings. So we have momentum P. This is now before collision. Before it has been hit by the X-rays. Now we have also the reflected radiation, this one which is being reflected. It has got, we forgot something here. This one has got wavelength lambda, and now this one, let us say the reflected radiation. This reflected radiation has got energy. Let's call it A, with a certain that one you can see, and it has got a momentum. Let's represent this one also with F. So it has got a momentum P sub naught F prime. So here we have F prime. So this one is moving with the frequency F prime. This one is moving with the frequency F. It also has got wavelength lambda prime. What else do we need in this equation? I don't see anything else that we need, but remember, when the electrons are stationary, we have their energy is given as m0c squared. That is the energy of electrons before collision, and this m0, where m0 is what? Is our rest mass energy. Okay, now let's start our derivation. From here we will see whether we've understood something or we've not. Now, let's start from here. We know that this wavelength is moving and therefore it acquires momentum. Now, if the momentum of this incident radiation, we say that it is what? PF. And then have a look at it. PF, this one, momentum of this. And then we have the reflected one, prime, F prime. They interact at a certain what? A certain angle. So we have this, we can draw something like, we have, so this one was the reflected, the incident was coming this way, and then we've extended some line, then we drop this one. So we can say that this one is PF, and then this one is what? PF prime. Now this one is theta. We can see that they are interacting at a certain angle. So when we multiply, when we find the dot product of this incident momentum and reflected momentum, we will get, we have PF dot PF prime. We will have, because they are interacting at sorry for that interaction, because they are interacting at this angle, we will have PF prime, then we have what? Cos theta. Let's call this one our equation 1. Hope you are together. Now, let's come back here. This X-ray obeys 2 laws. One, we have the law of conservation of energy. The law of what? Of conservation of energy. Now, we have the energy of the incident ray of or radiation. Its energy was what? EF. We said it here, somewhere here, this one. And then, now we compare it with the electrons. So this energy or radiation, we can call it photon. Those electrons, those radiation which are moving, X-ray radiation, they are particles, photons. So law of conservation of energy, that is for photon, electron, photon, electron system. You compare the energy of electron and photon, right? So this one is the energy of the photon or radiation which was released. And then compare it now with the energy of the what? Of the stationary electrons, which was in the target here. So its energy was what? Plus MO, its rest energy. MO, M naught, can say M naught squared. So law of conservation of energy says that energy before collision and energy after collision is what? Is equal. So energy of incident photon plus energy of the electron at rest should give you now energy of what? Of photon which has been reflected, E F prime, and then plus energy of what? Of electron which has been reflected. Let us call it E that way. Okay, so sorry, we forgot here. This is after collision. After collision. Sorry for making that mistake. So plus E. Hope we are still together. Now, the second law is the the law of conservation of linear momentum. Linear momentum. For what? For photon, electron, for photon electron system. Now, momentum before collision was what? We had PF. So momentum before collision was P sub F. And then now plus momentum of electrons before collision, we have P, should give you what? Momentum of photon after collision, we have P F prime, that one, plus what else? Plus momentum of electron after collision, P. Let's call this one P prime. But since this electron is not moving before collision, its velocity is what? Its velocity is 0. And we know that P is equals to mv. Now, if velocity is 0, meaning P will be 0. So we have PF is equals to P F prime plus P. Okay, let's call this one equation, we forgot this one. Let's call this one equation 2, this one equation 3. Hope we are together. If you lost, you can rewind the video and follow keenly before you reach at this point. Now, the next step, we want to rearrange equation 2. You rearrange equation 2 and do what? And square. So we have EF. We can bring this one on this side, minus EF prime plus m naught c squared is equals to E. But we've said you rearrange and square. So we have this one squared and then this one squared. Now, from there, we can rewrite this equation in momentum form. Is that possible? Let us see. We know that energy is equals to HF, right? Energy is equals to HF, and F is equals to C over lambda. Now energy will be H C over lambda. Now let us see. If we divide here by C, we see that energy over C is equals to H over lambda. Are we together? Are we together? So this is what we are getting now, but we want to represent this one in terms of what? Momentum. Okay, let's continue. We know that energy is equals to mc squared. Energy is equals to mc squared. Now, we want to find momentum here. We can write this equation as energy is equals to mc dot c. mc will give us momentum. So we have E is equals to momentum times c. We divide by c, we divide by c. So we are getting that momentum is equals to E over c. Are you seeing that? Yes. And here we also found that E over c is equals to h over lambda, meaning momentum also is equals to h, which is Planck's constant, out of lambda. Now, let's rewrite this equation. in form of momentum. Let's rewrite that equation in form of momentum. And our equation will be, this one is E, this one is E, and if we replace P here, meaning C will have been divided all over. Yes, so we will have EF minus EF out of C minus EF prime out of C. And it's okay. And then we square, then plus 2m naught C. Sorry for that interruption. 2m naught C into EF out of C minus EF prime out of C squared. So this one should equals to what? P squared. Okay, all right. Now, from this equation, we know that E over C, let's look here, E over C is what? Momentum. So we can replace this with the momentum. So we will have P F minus P prime F prime, we square, plus 2m naught C into PF minus PF prime should give us P squared. Oh, I'm writing S instead of squared, sorry. So we have P squared. Now, to eliminate P squared, we want to eliminate this one. We turn the momentum to what? Momentum in this equation. Where is that equation? In this equation 3, we turn the momentum in this equation and square it. We rearrange this equation and square it. So we had in equation 3, we had PF is equals to P prime F prime plus P. So that is what we had in equation what? Equation 3. So we rearrange it to have P F minus P F prime is equals to P, and then we square it. So if we square this one, we will have squared. Now let's open the bracket, right? Let's open this bracket and see what we will have. If you open this bracket, you will have PF squared plus PF squared minus 2PF minus 2PF dot PF prime is equals to P squared. So this is what we have. This is what we are getting from expansion of this equation. We've rearranged equation 3 and then find the square on both sides. Now what is our next step? The next step is checking. We have this one here. We saw that when we were starting, let's come back here. We have PF dot PF prime F is equals to, it gives us this one. So we can rewrite this in terms of cosine, so that we have PF squared plus PF f prime squared minus 2. Now this one times this one, we found that it gives us pf dot pf prime, that one, cos theta is equals to p squared. Now let's call this equation, this one was equation 3. Let this one be equation 4, and then this one be equation 5. Now let's compare equation 4 and 5. Equation 4 and 5. These equations are equating to what? P squared, meaning we can equate equation 4 to equation 5. So we have PF, that one is for equation 4, minus PF minus PF prime squared plus 2m naught c PF minus PF prime is equals to, now equation 5 we have is equals to PF squared plus PF prime squared minus 2PF PF prime cos theta. Sorry for lacking enough space to extend this one. And from there we can also expand this equation, right? We can expand it. This now just kucheza tu na algebra, define some values. So we have PF squared plus PF prime squared plus, no, minus 2 PF prime plus, now this one, 2 m naught c into PF minus PF prime is equals to this one, is equals to P square F plus P square F prime minus 2 PF prime cos theta. Now from there we can see that this one is the same as this one. We cancel them out. This one and this one are equal, so that we remain with negative 2 PF P prime F prime plus 2 m naught c into PF minus P F prime is equals to, on this side we only have negative 2, that space won't be enough, so we have negative 2 PF prime cos theta. Now we can cancel some things out still, because we have 2, 2, 2, 2. Can decide to divide here by divide by 2, negative 2 P F P prime F prime divided by negative 2 P F P prime F prime divided by negative 2 PF P prime cos, I'm lacking space, cos theta. All right, now This one will cancel out, we'll have 1. This one, 2 will go, so that we have a negative m naught c pf minus what? Minus we have p prime f prime, then out of mc naught is equals to we have, if we divide this one, no, we were not dividing by cos, I'm sorry. So this one we'll only have cos theta. Okay, all right, so far so good. We are finishing, we are about to finish. Now from there we can rearrange this equation. We take this one the other side, this one this side, so that we have 1 minus cos theta is equals to m naught c. Oh, we divided here by mc naught. It's supposed to be this one. So we have pf prime f, that one. So we have pf minus p f prime out of pf prime. So if we divide, sorry for network disconnection, but let's continue. We divide this one by m naught. In this equation we divide by m naught c, so that we have on this side we'll have 1 out of m naught c, 1 out of m naught c into 1 minus cos theta, into 1 minus cos theta is equals to pf minus p prime f prime out of pf f prime. All right, now if you check this equation, this number here, you can see that it seems it was a fraction which was subtracted. Let us say this now requires calculation, mathematic concept. We have 1 over pf prime minus 1 over pf. If you calculate this equation, you will find this number here. So this one just requires some calculations, so that you'll have 1 over m naught c is equals, in bracket 1 minus cos theta is equals to 1 out of p prime f prime minus 1 out of p f. All right, hope we are together, mtu hajapotea, you've not lost. So what next? We've come all along, so we want to derive now the h. So from there we can see that we have pf prime and pf, and then there is an equation that I showed you earlier on, this one here, whereby we say p is equals to h over lambda. So we can apply that one here, where we replace h and lambda where necessary. So we have this one, we will have, if you replace here with, now lambda here will be lambda prime, but here will be lambda. So here we will have 1 out of h out of lambda prime minus 1 out of h out of lambda. We can rewrite this one to be lambda prime out of h minus lambda out of h. Okay, now we can rewrite the equation, this one here, to we have 1 out of m naught c into 1 minus cos theta is equals to lambda prime out of h, or we can say let us say 1 out of lambda minus lambda, 1 out of h I mean, which is Planck's constant, into lambda prime minus lambda. Now because this h we can multiply here by h, this side by h, so that we get lambda prime minus lambda is equals to h over m naught c into 1 minus cos theta, and you're done. Yes, what is still remaining? You have the lambda. So this one is the lambda, the wavelength for reflected photon or radiation. We say that it will be greater than the incident, and this one proves it. We say that the incident wavelength of the photon is less than the reflected wavelength of the photon. Now from there we can give some parts some names. So this one can be change in lambda. This one here, we call it Compton's shift. This is the Compton shift. Lambda prime minus lambda, we get change in lambda is equals to h, not h, but lambda c into 1 minus cos theta. I'm sure someone is wondering, where is this cos lambda c from? This has just represented h out of m naught c, and it is called Compton's wavelength of the electron, where lambda c is equals to h over m naught c, and it's what? It's the Compton wavelength of the electron. It is the Compton wavelength of electron, and it is always given like 0.00243 nanometers. So far so good. So if you're told to derive the Compton shift equation, this one is the equation. This one here, that one is the equation. So thank you so much for giving me your time. If you have got any question, we came along, we did that, came from above, we found the momentum, everything, and so on and so forth. And that is it. Thank you for this video.